Alon Dogon, who will talk about effective stability for the lamplighter.
Hi, can you hear me? Okay, so first of all, thank you, Yotam, for speaking earlier. We all appreciate it. Let me say a few short story about Alex. So, okay, the pictures here are from, I'm copying Uwi's idea, right? I'm showing Alex's spirit, and here he's scrambling while being, I don't know, 69 maybe? Which is not trivial. You also see the bromance between Uwi and Alex. But, so these are some great events, and in the future, if anyone wants to join this, please contact Michael Glasner or Uwi. These are fantastic workshops. But short story I have about Alex is that I got married recently, just the day before Passover Eve, so it was during the war. I mean, the last round. Last round. And, right, so we were able to do it because we did it remotely on Zoom via Utah. And our officiant, so Utah law just says that only the officiant, the guys that conducts the wedding, needs to be physically in Utah. And we had a fantastic, I guess, Mormon officiant from Provo, Utah. So I had no idea where is Provo, Utah. But Alex told me that after the wedding, he has a great story to tell me about Provo, Utah. So first of all, okay, I learned from Michael that Provo, Utah is somehow a suburb of Salt Lake City. But Alex told me that the mayor of Provo, Utah once visited him in a flat at his home and invited him to celebrate the 4th of July with him in Provo, Utah. And Alex not only did it, but okay, he had some other reasons to be in Utah, and they went to a Beach Boy. The celebration was a Beach Boy concert. And it's a great story. I won't steal it, so it's a story. But you know, the fact that Alex was in the wedding and had this association is only because he's Alex. All right, so let me see what's time, so I get a rough estimate. Right, let's speak. Right, so today I want to kind of talk about a joint work with Thomas Vidick, but it's also like inspired by questions I was originally asked by Owen Beckel, who was mentioned today, not today, but on Sunday, and also previous joint works with Itamar Viktorovich and Aryeh Levit. But I kind of want to give a short survey of known results about what I think Michael Chapman coined the term effective stability, and then work towards the new ones. All right. Right. So what stability is an overused term, but for this talk and many of the other, maybe some of you heard this being thrown around. Most questions are somehow around this general question that Ulam posed in the beginning of the 20th century, which asked, when are approximate group representations close to true representations? Right? And in a second, we'll see how it's kind of, he's asking about probably approximately correct things. Right? So, but like, okay, this is one way to phrase the question, but something that is more recent and, okay, not really recent, but this question can be formulated equivalently as follows. When are approximate matrix solutions, but matrix here can be replaced with many things. Some people care about permutations, right? When are approximate matrix solutions to group equations close to actual matrix solutions, right? And the reason for this, I won't write it down, is that groups have presentations, right? Groups are defined by group equations, and being a homomorphism is like satisfying the defining relations. So you also have like an approximate, you should have an approximate form of this statement, right? But, all right, this slide is a bit technical. You don't have to understand the general definition. There are many competing forms of definition for stability. In a second, we'll see just examples and with like exact elementary examples that you don't need to understand this. But let me go over it quickly. Fix a finitely generated group. I will be interested in infinitely presented groups. So R here can be infinite. So let me define a local defect for a map and a global defect. And in this term, stability will be local to global, right? You want, if you have small local defect, you should have small global defect, right? And this I think Olin first did, right? So if you have a map, BSR is the notation for the ball of radius R in your Kelly graph. If you have a map defined on the ball to a unitary group of a finite dimensional Hilbert space, the point is like we want this definition to be independent of dimension, so I'm purposefully writing H and not like some D, right? So it can be of any dimension. The local defect of the map is just simply how multiplicative it is on the ball. Right? So it's the maximum difference between phi g phi h and phi g h. Of course, I didn't specify the norm here, but again, you can put basically any measure of distance you want here. In a second, I'll specify. So this is the local form. Like this is actually something you could check, right? I give you a map, you go over the ball of radius r, and you try to check how multiplicative is your map. The global defect is something that is harder to check because it involves actual representation. So it asks, it's a min-max thing, right? So out of all actual representations to your unitary group, which one is closest? Or what is the closest you can get to an actual representation?
Is it run over all dimensions? Like all
Yeah. No, sorry. So here it's the same. Of course, there are variants, but for this talk, it's to the same dimension. It makes sense to like let you enlarge the dimension a little. It's called flexible stability. Francesco could have talked about it, but he didn't. Yeah. Anyway, so gamma is stable if you have small. So notice the local defect depended on two things here, and that's because I'm interested in infinitely presented groups. It dependent on the generating set, but also a radius you fixed, right? So stability would say that for every kappa, there should exist delta and positive and a real number and a natural number r, such that if your r local defect is smaller than delta, you should be kappa close to a homomorphism. All right. Any question about this definition before I move on? Sorry? Yeah, so phi here should be generic, and for all dimensions, for this to be not. Okay, fantastic. So here's a bit motivation, and what's more motivating than the fundamental paper of von Neumann, right? So in this paper, von Neumann is trying to reconcile, right, Shmuel in his talk said that we never can be precise, right? We're measuring things, but we always have some error. And this is somehow witnessed fundamentally in quantum mechanics, right? Where you can't measure position and momentum of a particle simultaneously. And von Neumann many people were bugged by it, and von Neumann is trying to explain why. So, this is a paragraph taken from his paper on this topic, but let me like focus on the highlighted part. So just for reference, P and Q are these two quantities that you can't really measure simultaneously. And why is that? He explains it's because they don't commute as operators, right? In fact, let's look at the red part. The commutator is a non-trivial scalar multiple of the identity, right? But this scalar is really small. H bar, like, it was hard to observe this kind of stuff because H bar is really small. They almost commute, right? And then von Neumann says that, okay, because H bar is really small, assume that there are two other truly commuting operators, Q prime and P prime, whose difference from Q and P is small. So small that it's kind of, how small it is, the difference is governed by H bar, right? So the more they commute, the more you should be able to approximate P and Q by true commuting unitaries. And okay, the articles goes on, but he kind of, if you read it, you get the idea that he's saying that operators which satisfy the canonical commutation relation, you should be able to approximate them by truly commuting operators in some sense. Of course, here this relation only holds in infinite dimensions. I mean, it's kind of, you should be working with unbounded operators, but the same question holds for finite dimensional unitaries, right? So
the title, proof of the, am I reading it correctly?
Yes.
Ergodic theorem. Is this the paper in which he proves the L2 ergodic theorem?
so it's a good question. I didn't look for it, but you should have some ergodic theorem. There's also the scope for Neumann theorem.
No. Well, there was
Yeah.
a big
It's an
controversy
algorithm.
between him and Berkov. This is probably another paper.
He
Right.
has LaTeX?
Right?
Did for Neumann have LaTeX? That was
Yeah, sorry, I blurred out the translator's name. Yeah. This is on archive. Yeah, you can find it on archive. Just Google von Neumann proof of the H-sphere, whatever that is.
Do you know what sort of ergodicity does it do?
Again, it's good to look at papers of really smart people, right? So it's good to have a look at it. It's on archive. It's in English. You can. I just took a very, like this is a paragraph, right? And kind of already predicted. I really do think that he was the first one to pose this question of like almost commutativity between operators. And of course, after him, there has been a long tradition of studying this. I put von Neumann, but there should also be Halmosh, which asked this question. Ulam, and also Voiculescu played a central role, but Lean kind of Lean was, Joachim Lean proved like a celebrated theorem that almost commuting finite dimensional Hermitians are close to commuting Hermitians. But for today, the thing that is closest to me is a theorem of Gillespie, which is unpublished, but it's on archive again. But it says a beautiful statement. Let's look at it. So it says that for every kappa, positive, a target error, kappa will always be my target error. If you take delta to be polynomial in kappa, kappa to the ninth, more or less, and you have two unitaries which delta commute, then they are kappa close to truly commuting unitaries. Now, caveat here, you see that I'm putting HS under the norm. I will define it later, but this is not the operator norm, right? This is what's called the 2 norm. It's analog to like the L2 norm on the probability space, right? It's the normalized trace Hilbert Schmidt norm on the matrices. So HS is Hilbert Schmidt. And so Gillespie essentially tells you that in the group theoretic language, right, is that Z squared is polynomially Hilbert Schmidt state. Right? So he doesn't just say that almost commuting matrices are close to commuting matrices. He says he actually gives you the rate. And by the way, for Neumann, kind of, if you look at, I think this is this equation, like the spread delta Q delta P equals H bar over 2, he kind of also claims something about the rate of like how commuting you are versus how close you are in a later paragraph. Right, so Gillespie kind of says that this is true, but warning, Voiculescu showed this is not true if you put the operator norm. If you want to know why, ask Shmuel. Right, so this was one motivation. Before this attractive thing, let's just the statement above, I wanted to mention Oren's work. So Oren Becker and Jonathan Moshaev, they showed that the same is true. So a polynomial rate, this was first observed like qualitatively by Arjantseva and Taunescu, but which kind of started the subject for Alex. But Oren and Jonathan managed to show a polynomial rate via Ornstein-Weiss quasi-tiling techniques that it's the same statement is true for permutation. Permutation matrices instead of general unitary matrices. Yeah, so this is also a beautiful work. Now, let's pass from like quantum mechanics to quantum information. Right? Here we like binary observables. So instead of just general unitaries, we like unitaries who have order 2, right? Because that's somehow closer to what's called a bit or a qubit. Right? You only have two eigenvalues. And in this paper of Chow, Reinhardt, Sutherland, and Thomas, they kind of proposed a, I would say, operator algebraic definition of what is a qubit. So what is a qubit? A qubit is simply a pair of anti-commuting unitaries of order 2 on your Hilbert space. Why is that a good definition? Because that's a good definition because you can show that two matrices xz, which anti-commute, generate a copy of M2C. It's like two-dimensional matrices over the complex numbers. And this is kind of a, instead of working with Hilbert spaces and working with algebras, this tells you that you have a, say if you have two such things which commute with everything else, it tells you you have a tensor factor of M2C, right, which is like what we can work with as a qubit. Right? So, so in this picture, again stolen from their paper, they explain, but let me explain verbally, the left-hand side here is like a perfect 5-qubit system, right, where you have 5 copies of C squared, so M2C, tensored with each other, so they all commute with each other. And here you have a picture where you have qubits which slightly overlap with each other.
So
right?
it's separation and correlation.
Sorry?
It's a separation and correlation, as in a transfer.
Yeah, I missed that, but I trust you. Yeah. I somehow will mostly refer to Shmuel's talk. Somehow I was, I had more coffee then. So, yeah, so kind of the goal, or what they wanted to understand, is 2 questions, right? First of all, like, okay, n qubits, right, and this is the power of quantum computing, lives in an exponentially dimensioned space, right, 2 to the n. Sorry, the dimension is 2 to the n. But you can ask, oh, can I pack qubits into a much smaller dimensional Hilbert space with small overlap, right? So they want, but on the other hand, you should say that overlapping qubits should give, or slightly overlapping qubits should give you an exponentially dimensioned Hilbert space. And this, by the way, this point is crucial to the MIP star equals RE proof, because part of what you want all the time in Michael's compression theorem is to guarantee a lot of entanglement, or guarantee that your players are using a very large Hilbert space, or larger, exponentially larger than what you would want. And so essentially what you would need is a very efficient test of when slightly overlapping qubits actually give an exponentially dimensional Hilbert space, right? So this naive question is actually like variations on it, right, which I don't have time to get into, are fundamental to the techniques going into quantum complexity theory. But here is the theorem that they prove, which is, do I have, yeah, maybe let me skip this statement. It's a statement about almost commuting projections, but it's the same thing about almost commuting binary unitaries, because a binary unitary is just the difference of projections. So let me state it this way. They show that if you have k unitaries, which square to the identity, also this relation can be approximate, such that their commutator is epsilon over k small. Epsilon here is now your target error. Okay. Then there exists pairwise commuting binary unitaries such that they are epsilon close to your system. So what is the important factor here? Okay, this is a linear statement, right? You had epsilon here, you had epsilon here. But of course it depended on how many qubits you're testing, k. Right? And this is what you should maybe keep in mind when contrasting with the lamplighter result. How much time do I have, by the way? More or less?
Started at 50, about 35 minutes. So 20?
Sure.
Including questions.
I'll try to do it shorter. Not rush, but give people some time. Yeah. So what is the theorem that me and Thomas worked on? Right, so I'm just mentioning the group, although it won't come into the statement. The group we're kind of interested in is an infinitely presented group. right? By the way, this statement you can kind of view, right? Gillespie's statement was about a torsion-free abelian group. So that's one way in which an abelian group can be large. And this statement is about an infinite dimensional torsion abelian group, right? This is about Z2 to the infinity. So this is the other way an abelian group can be large. And the lamplighter is somehow a non-commutative mix.
In some sense, what you show is that it's not stable in the way that you want.
So
It's Z2 to the n.
So it is stable as it will be stable. I just didn't define what is an infinitely generated stable group. But however you define it, it will be stable because stability will only consider a finite set of generators. So it will be stable and efficient in some sense. I didn't define it, but infinitely presented is already like tricky enough. So right, this group, the infinite torsion group, is not finitely generated. The way to make it finitely generated is to introduce dynamics, right? You conjugate, you say that I have this infinite torsion abelian group, and I let Z act on it by a shift. The semi-direct product is called the lamplighter group or the reef product. This is a finitely generated group with just the Z direction and the single lamp group, right? But here's the statement just about unitaries. So what it is, given a target error kappa, now I need to also choose what I call my radius, right? We had a ball of radius something. So this will be polynomial in 1 over kappa, and my target error will also be polynomial. I can't guarantee maybe the exponents, but it should be something of this order of magnitude. Yeah, by the way, this is still work in progress, but hopefully it will be on archive soon. Yeah, so if you have two unitaries, A and T, so A here will be, you can essentially assume that it's a binary unitary, right? And the point is that the lamplighter relations should almost hold, meaning if you take your unitary A and conjugate it by T up to N, it will delta commute. Then I guarantee you an exact solution to these infinitely many relations, right? So A prime will commute with conjugates of it by T prime, like all conjugates of it by T prime.
Regardless of n.
Regardless of n, right? And they will be kappa close to your original proximate representation. Right, so it is important, I do want to mention that this theorem qualitatively, so without these polynomial bounds, was proved by Levitt and Migdalowicz, which in their study of characters on groups. And previously it was actually shown with, I would argue, a harder proof by Alex and Ariel Levitt, that qualitatively this is true for permutation groups. Right? And they were kind of actually the first people to observe that saying that this group is permutation stable gives you a qualitative statement of this form.
Sorry, is the HS normalized?
It's the normalized Hilbert Schmidt norm, again, yeah. I'm pretty sure that with unnormalized it's not true. Yeah. All right, so.
How it is normalized, exactly?
I will write it now. So I want to now, can I get rid of the presentation so I can write?
Try to do it.
Tom,
I'm
which
glad to
marker
see
did you
somebody
use?
using handwriting on the presentation like me.
No, seriously, you were the inspiration.
Limited.
So there? Well,
I think if you just press off.
So I try to press off, but
Yeah.
you say maybe it's a long off. Okay, it did work.
and how much time do I have left?
You have 10 more minutes.
10 more minutes. I won't take more than just.
Yeah. You can take rest.
Yeah. I just wanted to mention, right, let me kind of, I want to connect again to Shmuel's talk. Right, so, to cut the long, okay, I want to kind of cut the long story short, but when you have a semi-direct product, right, there's kind of an obvious thing to do for representation theory of it, which I mean goes back to Mathematicae, which is to do a Fourier transform over your abelian group, right? So if I don't know, like
Both of them are abelian. Which part is the abelian?
so the abelian normal side,
Okay.
because this group is somehow dual to what's called the Bernoulli shift, which is a dynamical system, right? So you have now the direct product of z's, of z mod 2, which I will just write as bits, right? Let's call the space x. And now x is a Cantor space, right? And you have a homeomorphism of the Cantor space just by right shifting or left shifting, right? If you take a representation of this guy, restricted to here, then this is x is as a topological space, let's call this n, the Pontryagin dual of n, right? So we know the representation theory of abelian groups. It's governed by measures or projection valued measures on this guy, and I claim because the space is totally disconnected, I have an approximate form of this correspondence, right? So let me nonetheless give this definition because I think it's nice. So a measure mu on x is m delta invariant if the following holds. Can you see her? Okay. If I sum over all b, so I won't write it, but b, let's call it m defined. So m defined just means I'm from the finite sigma algebra of cylinder sets defined up to window m in your book. And I look at the L1 distance of how much the measure of B changes under L. I want this to be smaller than delta. This is what I will refer to as an almost invariant measure on the Bernoulli shift. So what you can show is that given a finite dimensional representation and taking this Fourier transform of it, once you trace out the representation, you get such an object. In fact, this object is not enough for our finitary analysis. We need to talk about almost equivariant projection valued measures. Right? I need to keep in hand the projections. But that's also fine. And once you do this translation, the stability question kind of becomes in particular to answer, given an approximately invariant measure on your Bernoulli shift, can I fix it to an actually invariant measure? Right? And here's kind of a situation where fixing an approximately invariant measure is very easy. Right? So your measure is defined on the whole space, but let's look at the tower inside your space. Right? So say B is inside X such that B is disjoint from LB, is disjoint from L squared B, so on, up to some height. This is what's called a tower in dynamics, right? So the measure is approximately invariant, right? So the measure of this is more or less like the measure of this, more or less like the measure of this, more or less like the measure of this. So it will be, the measure of B is more or less like the measure of the total thing, let's call it the tower, over B and height J. It's more or less like the measure of the tower divided by J. Right? What? Yeah, J plus 1, something like that. Okay. So, how do I fix it? I just declare the measure, my invariant measure, to be the measure, this number for each set along the way. Right? And you can do the same thing for projection value measure. So the problem becomes a very classical problem in dynamics of building Kakutani-Rochlin towers. I want a tower decomposition for my space. However, you might remember in a Godic theory course that the Rochlin lemma is stated for free, aperiodic transformations, right? And my transformation needs inherently to have periodic points because the periodic points here are exactly the finite dimensional representations. I need to approximate. In some sense, it was already realized by Arya and Itamar that the things that governs qualitative stability is the fact that any measure is a limit of periodic measures. So I need to take them into my analysis. So that's one thing. The other thing is you want your towers to have polynomial complexity, right? And this is, I think, an interesting thing by itself, and goes actually into the area of descriptive combinatorics or Borel combinatorics, which was initiated by Benji Weiss. The question is, how constructive are constructions in ergodic theory, right? Can I construct Rochlin lemmas, towers, and so on, which are effective? I can give them a description. And it turns out that you can formulate a Rochlin lemma, which takes all these, and also the quasi-invariant measures, into account and prove it. But there's kind of a small thing which is called a marker lemma, which is kind of the starting point for all these constructions about building marker sets, which are like approximate fundamental domains, and that needs to be polynomial. Initially, we had exponential bounds because we just used a greedy algorithm to build a marker lemma, and Thomas, out of curiosity, I mean, I somehow didn't believe that it would be polynomial, and Thomas just asked chat, can you do it polynomially? And it did. But, as Shmuel said, it kind of did it by hand, right? But looking at it, I realized it was plagiarizing nothing, linear. So, and good thing I have a friend called Peter Narishkin, and with Brandon Seward as well, we've been, I mean, I was in San Diego and I absorbed a lot of this descriptive dynamics stuff, so I had context. And I realized it was doing an argument which I already knew from Brandon, from Peter, but it was never written down, so it's impressive. It's still ongoing another project, and this kind of effective thing is done via a algorithm of lineal, of Nati lineal, which says that if you have a graph with degree delta, and you give me some coloring of it, with like a huge number of colors, I have a very efficient color reduction algorithm, which within log star, so like iteratively log many steps, I can reduce the number of colors to like delta squared, something like that, right? And the fact that you have efficient local algorithms, which is, by the way, a whole study, and it's not new. There's works of Bernstein which connect local algorithms and Borel combinatorics. You can actually give an effective version of the Markov lemma, right? So this was kind of what Chat was doing by hand, but like you realize by context that it's like kind of okay, whether it's known or not, it's up to debate. But you know, like so you can it's part of a more general statement in context. So we actually beat it. I managed to beat its parameters by replacing something like L with log star L. Anyway, yeah. So that's the small connection to Shmuel, and let me end here. I think this is enough.
Questions to Alon?
So the lamplighter is very special. It's just a part of a general statement.
So that's for future work, and I do feel that, for example, another very natural semi-direct product is the Heisenberg group, right? If I look at the unipotent matrix acting here, this is H3. And this is actually a fundamental relation you need to correct, right? Are two unitaries which almost commute up to a scalar close, and okay, this is qualitatively correct, but we don't have effective bounds. I expect this to be polynomial, and I think that with enough, like with more dynamical input and understanding how to do the Fourier transform effectively, this is possible. I think this is, okay, so this example was like the baby, like the first example. It was like hard. There are probably some things there are already some things that we do in general. For example, the marker lemma is general for any group action on any Cantor space. But you know, there are some things, somehow the total disconnectedness of the space, I'm still struggling to get around to it, but the fact that this is the left shift is not so important. It could be any Cantor space homeomorphism, at least the dynamical limit. So there are like some parts which each part I can tell you more generally, but like this is the next example, and I plan to think about it, but
You want
yeah.
like semi-direct product of Hilbert Schmidt
So
stable stuff?
actually,
or
there's a
not?
beautiful paper of Rotem Yaari who shows that any meta-billion group of this form, which is finitely generated, is qualitatively Hilbert Schmidt stable. So Rotem is a student of Arye, and this is via, again, studying invariant measures, but as far as I understood from Itamar and Arye, already from like meta-billion groups or like two commuting torus automorphisms, this connects to like deep questions of Furstenberg about measure rigidity and so on. So it becomes a hard question. Right? So like even the qualitative question is hard.
So the minute that that side is rank 2.
Yeah. Yeah. Then it's problematic. Yeah. But the Bernoulli shift is really like the easiest example you can take to try to start understanding approximate dynamics, whatever that means, and then you need to think how to generalize this. But I believe this technique works for other examples.
You mentioned like semi-direct product. Do you expect like the semi-direct product of stable Hilbert Schmidt stable stuff are
So
stable or something?
stability of stability is a hard thing.
No, like
Sorry? Yeah, so it's not so, there aren't that many general constructions that would take two stable groups and give you a stable one.
Wait,
To
we
be-
know that the regular product,
Yeah, like
Yeah,
F2,
not an extra
F2
product,
times
just taking
F2.
out of anything that
I give you an example, right? F2,
Yeah.
F2 times F2, a product of three groups is not stable. However, in the amenable category, it's true. A product of amenable stable groups is stable, but you know, like whenever you, in the realm of amenable groups, stability is really a question about like harmonic analysis or dynamics of the group. But for non-amenable groups, there's a completely different story, completely different lecture that Francesco could have talked about. But yeah, like to do actual such analysis, so this proof uses amenability as well, if you think about it, right? I need that the measure of this and measure of this would be small if the tower is large. Okay, so it's really, proving one's group is stable, effectively stable, is really hard. So, yeah.
Even if you fix the group but change the norms,
Yeah.
can you classify the norms that give you stability and
I don't think anyone really seriously thought about that question, but really, like, once you change the norm, you change the subject. If you change to the operator norm, you're in the subject of algebraic topology, actually. You have, like, topological obstructions to stability. If you change to the unnormalized two norms, you are in the subject of Uri's talk. You're in vanishing of higher unitary cohomology. So again, like each subject, each norm kind of was anchored via some set of techniques, and it's really hard to connect them. Yeah, so the Hilbert Schmidt is like what I talk about here is really for this kind of approximately, probabilistically approximate kind of stability. Yeah. Okay, maybe we'll stop here just so people can take a break.